Okay, so today's lecture is on indeterminate forms and L'Hopital's rule. Okay, so what are indeterminate forms? Okay, so if you have something that is, let's say, infinity divided by infinity. We've actually seen this problem before, so this would be something like the limit as x tends towards infinity of, say, x squared plus 1 divided by x plus 5. Okay, so the top and the bottom are both headed towards infinity. We learned a trick earlier in the semester of dividing by the highest power of the top and the bottom, it doesn't really matter, to evaluate this limit. We're going to learn a new rule today, which is L'Hopital's rule. Okay? Other indeterminate forms are, let's say, 0 divided by 0, so that would be the limit as x tends towards 0 of sine of x divided by x. This is a very classical one. There's actually a very, I've talked about this before, but the limit as x tends towards 0, this guy is going to head towards 1, and it can actually act as a source function for wave equations. Okay. So with other ones, let's say infinity minus infinity. So limit as x tends towards infinity of, let's say, the square root of x plus 1 minus the square root of x. Okay. Once again, we've actually seen this problem before. Whenever you see square roots, you automatically think that you're going to use the conjugate trick on that one. So the conjugate trick applies to that one. Or let's say we have something that looked kind of like, let's say, 0 times infinity. So that would be the limit as x tends towards 0 from the right of x times the natural log of x. Now, if we send the limit as x tends towards 0 from the right, well, x is just going to tend towards 0. All right? But if you send the limit as x tends towards 0 from the right of the natural log of x, that's actually going to tend towards negative infinity. So we don't know if this limit is actually headed towards 0 or if it's headed towards negative infinity. So we're going to have to do some investigation to determine which it's actually headed to. Right? Or there are other ones like, let's say, 0 to the 0 power, which would be something like the limit as x tends towards 0 of x raised to the x yeah. Or let's say, I mean, you can end up with a lot of these. So let's say infinity to the 0 power, which would be the limit as x tends towards infinity of x to the 1 divided by x. Okay. And there's even ones that you wouldn't think would be indefinite forms, but they actually are. And so something like 1 to the infinity. Okay? I'm going to use a different letter on this one for a specific reason. So the limit as n tends towards infinity of 1 plus 1 divided by n raised to the nth power. So as you send the limit as n tends towards infinity, the interior of this problem, 1 over n is going to go to 0. And so the interior looks like 1, basically. And so, but you've got that n to the infinity right there. And so a lot of people would assume this just equals 1. That's not true. I can actually make this equal whatever I want to. This guy right here comes out to e to the 1. Okay. And we actually have a more general rule for this one. So if we say the limit as n tends towards infinity of 1 plus x divided by n raised to the nth power, this actually equals e to the x. And this might seem like a problem where you'd be like, why do we care about this? Okay? Well, the reason we care about this is this leads to a much larger problem involving continuously compounded bank interest, where the limit as n tends towards infinity of your initial investment, R is your interest rate, it is the number of times it's compounded. This actually equals P naught e to the RT. This leads to the formula for continuously compounded interest. So we'll prove this a little bit later on in the lecture, but if we have our principal amount, the interest rate on the bank account, the number of times it's compounded per year. So if it was compounded quarterly, n would be 4. If this was compounded monthly, n would be 12. If it was compounded daily, n would be 365. But if you send into infinity and say, oh, and t is time in years. If you send into infinity, then it's going to be compounded continuously, meaning every second of every day. Okay? Well, you have to be very careful when dealing with limits like this. As a matter of fact, I was goofing around on YouTube, and this is going to end up on YouTube, so I'm going to throw some shade at some YouTubers. I was watching a video that somebody had posted onto YouTube the other day, and they were evaluating the integral of x to the x, and there was not a limit anywhere in the problem, and it drove me insane. Because the person was evaluating an improper integral and didn't use a limit anywhere, which is absolutely wrong. And if they had been in my class, all right, let me put it this way. When we evaluate limits in Calculus 2, there's a lab on improper integrals. And if you don't put limits on your problem, you're getting an F. I mean, I just flat out tell everybody that at the beginning because it's wrong. And somebody posted a video that they didn't do very intelligent. And I'm just stuck. Anyway, okay, so how do we end up dealing with problems like that? We're going to look at book and tell. Okay, so if the limit as x tends towards a of f of x divided by g of x is of the form 0 divided by 0 or infinity divided by infinity. Oh, and this could be plus or minus infinity on top or bottom. Okay. Well, if this is of the form 0 over 0 or infinity over infinity, negative infinity over infinity, whatever, then what we can do is we can take its derivative at the top and bottom. The limit as x tends towards a of f of x divided by g of x is going to equal the limit as x tends towards a of f prime of x divided by g prime of x. Okay? So it basically means that if you can get it from infinity over infinity or 0 divided by 0, then what do? You just take the derivative of the top and the derivative of the bottom and then try to evaluate it from an